So welcome to today's webinar. My name is Matthew McKnight. I'm a technical specialist at Autodesk. Today we'll be talking about modal analysis with Nastran In-CAD. So let's get stuck into it. My details on the screen. If you'd like to contact me after the session, and if you've got any specific questions you'd like me to follow up on, please feel free to reach out via whichever channel you'd prefer. Otherwise, let's get into the content. So what is a natural frequency? Well, every item has, whether it's big or small, its shape, no matter what shape it is, will have one or more natural frequencies associated to it. So this is the natural frequency that the part will resonate at when it's excited by some sort of motion or force. A tuning fork is a primary example of one such item that vibrates at a particular frequency. But what you'll note is that even a tuning fork will have many different frequencies. So depending upon where you hit it will depend upon the frequency that you excite. So if you hit the tuning fork in the wrong area, you'll get another frequency. What this is often referring to is the clang of the object. It's where you excite a mode shape that is not the fundamental frequency of the object, but is one of the other associated modal frequencies of the geometry. And this is exciting, potentially multiple frequencies at the same time, possibly in combination with the fundamental frequency. And you can see here it will potentially excite a different mode shape, as there are many mode shapes. So why is it that we care about modal analysis and the natural frequency of our designs? Well, because in real life, objects that we design, no matter how big or small, will exhibit these types of characteristics where they're excited under specific conditions. The classic example was the Tacoma Narrows Bridge, which was excited as a result of wind loading, I believe, and which caused the bridge to then start to move in relation to its natural frequency, and as a result of that continued to amplify until basically fracture. So the key takeaway here is that no matter whether we're talking about bridges, maybe you're a fan manufacturer and you're looking at the rotating mass of an object that's running at a specific RPM. Maybe you design telescopes and you're concerned about the optical precision of your devices. Components will resonate at their natural frequency, and it's in our best interests to take this in mind and try and avoid operating our devices in those areas or looking at potentially shifting the natural frequencies of our designs to avoid these unavoidable loads that we could be imparting on the design. So what can we do about it? Well, a natural frequency can be calculated. So there's no need to go to the time and expense associated with building and then testing a part. We can virtually test for the natural frequencies of our designs using simulation. So let's have a look at how we do this. And this is where we're going to work through a quick example. And let me just open up Inventor to show you what we're going to do here. So here we are. We have a part from the tutorials or exercises section of the help guide. So if you're wanting to follow this through, then you can follow this through at a later time. Just download the files that are available to you. And what we can see here is we can then step inside of our Nastran In-CAD environment to set up this study. Now, as we've seen previously, whenever we enter the environment, it switches our model tree over, so we get the setup associated with our simulation. And by default, that's going to activate or turn on a linear static study. So in the first step to running a modal analysis is to edit that study type and change it from linear static to normal modes. And this is going to then switch us into the environment where we're looking for these natural frequencies of the part. There's nothing else that we need to do here in this instance. I'm just going to simply hit OK and then move on. One of the things that I'll point out as a result of making that change is now we get a modal setup inside the subcase. And you'll see that if we edit this, we can rename it, but we can also adjust the number of modes that we're looking for. In this case, we're going to use 10. If maybe we were concerned about a specific frequency range, maybe we knew that our motor was going to be running in a certain bandwidth of frequency, we could put the lowest and the highest frequency and then just look for mode shapes that are going to occur between that range. Let's just go OK and leave that. Let's make a quick change to our part. So I'm going to edit the physical property of our design and then make a quick change to our part. So rather than using the generic material, I'm going to use alloy steel, and I'm going to get that from the material database. So choosing alloy steel, go OK, and OK. And we've now reassigned, and we can confirm that by going up into the analysis 1, and you'll see that we have alloy steel. Realistically, all we need further to that is to constrain the part in some orientational fashion. So in here, I'm going to add a fixed constraint just to the inside face, the back of the part, making sure that we have all translations and rotations constrained, hitting OK, and we're pretty much set to go. So I'm going to hit Run, which will instigate meshing of our geometry. And once the part is meshed, then it'll switch into the Nastran output mode and cycle through generating the results of our study. So we'll give this a moment or two just to quickly solve. And it shouldn't take much more than that really, as running modal analysis is actually quite quick inside of Nastran In-CAD. You can see it's complete. It'll delete the file, and then it will tell us our solution is finished and put us back into the Nastran model tree environment. Okay, so what can we do? So I'm going to edit the results plot of this, and I'm going to look at some of our results. Now, in the first case, it's important to point out that the stress and displacement results associated with modal analysis can't be considered as real stresses and displacements. So if you turn on a displacement plot for the first mode, you're seeing here we're getting 290 millimeters of deflection. So please recognize that the mode and the mode shape and the mode frequency are accurate, but the accuracy of the displacement, stresses and strains is not. So please disregard those. If you're looking for those, then we can look at doing subsequent analysis using a different analysis type. So now that we've run this, we can look and see that the various different modes that have been output as a result, remembering that in our modal setup we went through and set the number of modes we want to look for. So we've got 10 modes, and then it gives us the specific frequencies that these are being activated at. And you'll note that there's something quite interesting happening here. So we're getting groups of 3 frequencies. So we've got 675 hertz, we're getting 677, 679. So around that 675 to 680 hertz, we're getting a group of 3 resonant frequencies. We're also getting the same here, so we're getting 1531, 1535, and 1537. And that makes sense because the hub of our propeller is quite thick and rigid and stiff, but we're finding that the blades of the propeller aren't and as such, though they are geometrically similar, and we get some discrepancy, most likely due to mesh differences in the meshes of each of the propellers. What we're finding is that we're getting a correlation between all of these propellers and the modal frequencies of them to resonate or excite at a specific resonant frequency. So So what we can see here is we can look at the mode that's taking place in this instance. So we can look at the shape that we would expect the part to deform at. You can see here that the tip is deflecting backwards and forwards. And likewise, if we looked at, say, the mode 2, which will be one of the other blades, then we should see a reasonably similar output as a result of that as well. You can see here at the top, we're getting a forwards and backwards resonation of the part. If we shift to an alternate frequency, say one of the higher frequencies, and we look at the animation associated with it, we might find that it's slightly different and in a different direction or characteristic. You can see here that it's twisting rather than displacing forwards and backwards. Okay, so once we've established these frequencies, a common question that comes up is, how do we know whether we have calculated enough mode shapes? Well, one way of determining that is to look at the output file from the study that's been run. So I've just shifted into a File Explorer, and we can interrogate the output file that's been generated. And here's what the output file looks like. And we can run down and find a specific area that we're looking for, which in this case is our percent modal effective mass. So here it is here. And this table is going to give us an idea of in each degree of freedom, so our 3 translation, T1, T2, T3 being X, Y, and Z, R1, R2, and R3 being the rotations around those subsequent axes. And you can see here that as a total of all of the mode shapes that have been generated, the percentage of effective mass. And what we can see here is that we're getting a range of percentages for each of those translations and rotations. But to understand whether you're getting a good correlation on a result, then what you should be looking for is to ensure that these are around 85%. You can see here at the moment, some of these are significantly lower. So what we've got R2 and R3, which are up around 35%, but then we're getting T2 and T3 around 2.5 to 3%. So what we should be doing in this instance is to try and increase the number of mode numbers that we're solving for, and then come back and trying to correlate this to ensure that we're getting about 85% as a value, which will give us an indication of whether we've got enough mode numbers. To do that, we would then just come back into Nastran In-CAD. We would edit the modal setup here, and then increase the number of modes that we're solving for. In this case, could be 20. I'm not going to do that. I'm going to step on through to the next section of our presentation, and that is to give a bit of a summary associated with what we've just found. And that is that, and one thing we haven't talked about is the relationship of our mode shapes and modal analysis to the maths and equations that are running in the background. So this is a classical eigenvalue problem for what we're seeing, and from this we can establish that there is a relationship between 2 real key parameters in this study. One is mass, the mass of our geometry. So without mass, there will be the natural frequency will be 0, and also stiffness. So if we have no stiffness, then again the natural frequency will be 0. So making sure that our parts are replicated in, as representative as possible will make sure that we're getting accurate results in this instance. And let's have a look at what happens in this case if we don't do that. And what I'm going to do is step through another example. And in this case, we'll use the same part, the same geometry that we've already set up. I'm going to make a quick change to the material that we're using. So I'll edit the alloy steel, and I'm going to quickly, remove the density of the material. So what am I doing here? Well, let's assume, say for instance, when we've gone and entered our mechanical properties for our parts, we haven't included density. And remember, density isn't required for certain study types like, say, a linear static analysis, where we're not taking into account things like gravity. So I can remove that material and run an analysis, and it'll be fine with the linear static. Let's see what happens if we do that in this instance. Hit run and see what result comes about. Okay, so it's at the end of the study, it's come back. It said the Nastran solution has failed. Let's switch back into the output and have a quick look at what it's telling us. And you can see if I expand out the panel, it says here, fatal error, non-zero global mass matrix required for analysis. And that gives us a reasonable hint as to what's going on here. But if you want some further insight, then if you click on the code, the error code associated with it, it'll actually bring up the Nastran help and find that error code and then give you some further insight. So if we look at the action, it says here, correct the applicable material bulk data entry by specifying the material density in consistent units. So you'll hear it's quite clearly saying to us that we need to go and make sure that we've assigned the material correctly with inside of our setup. So if we go back to the model tree, edit our material, and then put in our value for what our density is, then again that should solve that problem and run sufficiently. Okay, so let's have a quick look at some further info. So what happens if we solve this? Well, if you do solve it, and it still will solve by running the modal analysis, it will actually solve, and you'll find that the results will come back as 0 as well. Whereas static problems can't be solved using this same technique. And that's the problem, is that we can actually use, or that's part of the advantage of using a modal analysis, we can actually use it to debug some of our static analysis studies and understand some of the reasons behind potentially what's going wrong with them. So let's have a quick look at this in this instance. So I've got another example that we'll step through, and let me just go back into Inventor. And what we're going to do is assume, say, for instance, that we are going to run not a modal analysis initially, but let's just run a static analysis, linear static analysis. So I've changed that over. And what I'm going to do is underdefine or underconstrain the part. So rather than fixing it completely, I'm going to edit that constraint 1, and I'm going to turn off all the translation. So that means that it's restrained from rotating but can translate. And then what we can do is we're going to add a force and a pressure. So I'll add a load. I'll choose the direction and the face that I'll apply the load. We'll apply it in the X direction, so we want it through the axes. And we'll apply a 10 kilonewton load. Just make sure we turn it on so we can see where it is. There it is in there. Go OK. Let's now apply a pressure, maybe onto the front faces. Of 10 MPa. Just make sure that we've got them in the right directions. Yep. Go OK. So now what we've got is we've got a part that we're trying to analyze under a linear static load. We've underconstrained it purposefully, but we may not have realized this in the process of creating it. So let's run this study and see what happens. And this shouldn't take too long to solve. It should be quite a quick and easy process. Okay, and it's come back and it said the Nastran solution failed. And if we look at the output file, you'll see here that it's saying fatal error 5000 singularity detected at grid 3203 component 3. So this doesn't necessarily give us as much insight as we might need. We could go and look at the help guide and try and understand. You will see here though that it is suggesting that check your model for a lack of constraint. So how can we do that? Well, one really valuable way of using modal analysis is to use it to look at the constraint of your part. So if we go into our Nastran model tree, and I'm going to change the study type to a modal analysis or a normal modes and go OK. And other than that, all I'm going to do is hit run. So I don't have to, change any of the settings. Note that in using the modal analysis or normal modes analysis, it's not taking into account the loads. So it's considering constraints and then the stiffness and mass of the part, but it's not taking into account the loading conditions that we're applying. But this is going to help us then look and try and understand what's taking place in this case. You can see here it's completed, and as we said a little earlier, even if you've under-constrained your study, like we have in this case, it will still complete. The interesting thing is that can be found when we go and look at our results. So if I edit our results plot and then look at our mode cases, you can see here that the first 3 cases, actually the first 6 cases, are pretty much 0, as in the natural frequency of the part, or the modal frequencies of the part, are showing to be 0, or effectively 0. So what we can do is, say if we wanted to look at a displacement plot and display the animation or the displacement, you can see here that we're getting displacement that's non-typical of what we would normally expect having done this. And one interesting way of just determining what's happening is to switch on our displacement plot, but then look at displacement along the various axes. So if I look at, say, displacement along the z-axis, you can see here that I have zero displacement in any of those, any of that direction. You'll see the same for y, but then when I go to x, subsequently I get significant displacement, which is suggesting to me that my part is under constrained in the x-axis. So there's something that's there's some setup parameter or constraint that hasn't completely constrained the part within that direction. So what I would do then is, obviously, then I would go back. I would edit my plot, change all my study type back to a linear static. I would go in, assess my constraints, either adjust the existing constraints or potentially add subsequent constraints to ensure that I'd constrained my geometry correctly, and then rerun the analysis, and you should find that that should run now. Okay, let's go back into our presentation and just quickly finish up. So why do we care about modes? Well, it's going to help us get a better understanding or a deeper understanding associated with the model's dynamics. So it's going to firstly tell us, is my problem really dynamic? And it's also going to give us an idea as to whether the results that I'm getting or seeing are within inside the ballpark. We can validate the results that we're getting using books such as Formulas for Natural Frequency and Mode Shape by Robert Blevins. But it's also a lead-in to some more advanced dynamics problems. So we could run, say, a modal analysis initially, or a normal modes analysis, but then run subsequent analysis to look for true stress, true displacement. And it's also highlighting, the frequency range of our parts where we might have critical frequencies that we want to try and avoid, or adjust the geometry to try and shift those frequencies away from. If you want to run more advanced dynamic analysis, then we can look at other analysis types like modal frequency response or modal transient response, and there's a whole range of different response analysis types that we can run for dynamic problems. Otherwise, I'll wrap it up with that, and I will highlight some further reading. So if you're looking to find out some more around Nastran In-CAD, the Autodesk forums are full of fantastic information. We're getting a lot of contribution from our customers and users, and you'll find that they're not only talking to one another but talking to a lot of the support staff directly within Autodesk around Nastran In-CAD. If you're looking a little bit more broadly than that, I suggest you follow the Twitter account for the Autodesk simulation team, or the Facebook account for Autodesk simulation, as they update quite regularly all the latest happenings with the simulation solutions. And you might also find that on YouTube there's the Autodesk Sim 360 channel, which has got a whole bunch of videos that are being uploaded around simulation and simulation capabilities. Further to that, and a little bit more closer to home, you'll find that the Future of Making Things LinkedIn group, we're posting regularly updates to updates that are around trends and technologies that are affecting manufacturing, particularly in Australia and New Zealand. So if you're on LinkedIn, please make sure that you join that group and connect with us and participate in the conversation. Otherwise, if you have any further questions after the session, feel free to contact me on the contact details shown here. Let me have a quick look and see whether there are any questions to follow up on. None at this stage. So what I'll do is I will call it a day. Enjoy the rest of your afternoon, and hopefully we'll see you next time. Bye for now.